A function f with domain D is a rule which assigns each element x in the domain to a single number, which we denote f of x. The domain is usually a set of real numbers, and the range of f consists of all possible numbers of the form f of x, with x being in the domain. So the domain are all the possible inputs, and the range are all the possible outputs. Now, functions are really important. They're one of the most used and most critical things we have in mathematics. To denote them, we usually use f of x if f is available, but many different letters are often used. We'll use y, g of x, h of x, and etc. And these additional letters are used if I use more than one function. You can think the domain of functions as all the possible allowed input values, and the range is all attainable values of y. Now, when we represent these functions, there are so many different ways. We can represent them algebraically. We can represent them visually. We can represent them numerically. And we can represent them verbally. If you go on to higher level mathematics, sometimes you will prove that functions exist that you can't represent algebraically, but they're a function and they do exist. And there's no real way to visualize them, and we don't really have a table of values. And we can kind of describe them, but not great. But we know it's a function, we know it exists. We're not going to deal with those for now. We're mainly going to focus on functions that you can represent algebraically, visually, numerically, and verbally. By the end of this course, you should be able to take an algebraic description of a function and accurately represent it visually. This process is often referred to as curve sketching. And this curve sketching is going to be a big process that we learn and focus on within most of your calculus classes. Now that we've defined functions, we want to talk first about visualizing them on graphs. And it's tempting to say that these pictures that we have here in our example are lines, but we just defined a line as a straight drawing or something that's straight. A line is completely straight. So we actually call these curves. So there's a little curve to them. And with curves on the xy plane or the Cartesian plane, we want to ask ourselves, are these curves functions or are they not functions? And the way that we determine that is we use the vertical line test. And the way it works is the curve is a function if and only if no vertical line passes the curve more than once. Okay, so if we look at all of our vertical lines, we're asking ourselves, do we cross once or do we cross more than once? Now, when we're asking, do we cross once, we could cross never. So we could have vertical lines that never cross. But we really want to know, do we cross at most once or more than once? So in this first example, well, this line crosses twice. So this is not a function. Whereas in our second example, we only ever cross at most once. This is a function. Here, we only ever cross at most once. This is a function where here I cross twice. This is not a function. Now, in higher level mathematics, when we are given a function, we're typically given a domain. The domain is typically specified. But in calculus, we often use the natural domain, or the domain that naturally arises. Now, what is this quote unquote natural domain? Well, the natural domain of a real valued function are the real numbers that make sense. And the numbers make sense because they do not break any math rules. Now, the three main rules to determine our domain restrictions, or the three main ways we break math rules, are dividing by 0, taking the square root of a negative number, or the log of a non-positive numbers. And we're just going to highlight these. And typically when we're thinking about our domain restrictions and trying to build our natural domain, it's helpful to think about what we're not allowed to do. And when we highlight what we're not allowed to do, we take everything else. So the first thing is we cannot divide by 0. So if f of x equals g of x over h of x, then h of x does not equal 0. So we figure out where h of x equals 0 and say everywhere else. We also cannot take the root of a negative number. So if f of x equals the nth root of g of x, then g of x cannot be less than 0. And we cannot take the log of a non-positive number. So if f of x equals log base b of g of x, then g of x cannot be less than or equal to 0. Now we take the interval that satisfies all the constraints. So when we're looking at a function, we write out all the constraints, and we take the interval that satisfies all of them. So we're taking intervals, we define these intervals, and we satisfy all the constraints, or we intersect all the intervals. Now, I highly encourage you, if you don't quite get the intersection of the intervals, there was a review we did earlier in one of the previous videos that goes over the intersections of intervals. We're now going to compute the natural domain of 3 of the following functions. Now, our first function, f of x equals x squared minus 1 over x minus 1. Here, x minus 1 cannot equal 0. X cannot equal 1. This is my first constraint. Now, it's also my only constraint. This tells me that x is in, actually, let's draw this on a number line. Everywhere except for 1, I'm valid. So x is in minus infinity to 1, not including, so round bracket, union with 1 to infinity. Let's take a look at our second example. F of x equals the square root of x minus 1. Well, here, because of my second rule, x minus 1, the expression inside, cannot be less than 0. Well, the opposite of not less than 0 is greater than 0. So x minus 1 is strictly greater than 0. Here, using the split point technique, we isolate our split point as 1, x minus 1, positive, negative, positive, and this is greater than or equal to 0, and I am 0 at x minus 1. So this is at 1 and bigger, so x is in the interval 1 to infinity. Okay, and my third domain, or my third function, is f of x equals ln of x minus 1. Well, here, because of my third rule, x minus 1 cannot be less than or equal to 0, which implies that x minus 1 is greater than 0. Again, creating this using the split point technique, I create the graph. plus times 0, 0, minus, plus, minus. Here, because I have to be strictly greater, I'm not using the 0. So my x is in domain 1 to infinity, excluding 1. Now, you might be looking at these intervals and say, well, I can solve these without using the split point technique. And you can. The reason why I always use the split point technique is it's one technique that always works. You don't need to use it. If you can solve the inequalities a different way, that's fine. But I like using the split point technique always, because it always works. Also, practicing it for these simple examples will help you when fundamentalize it for when you get to the harder examples.